Welcome back. This is the continuation of the full work solutions to the Nature of Light worksheet 4A. Previous videos have gone through questions 1 through to 4, 5 through to 9, and this one here we're going to go through questions 10, 11 and 12. Okay. So having a look at question 10 now. A muon, which takes 5 milliseconds to decay in the laboratory, so that's the time when it's stationary, is observed to decay in a longer time in 6.8 milliseconds. So that's the dilated time. What would be the speed that the muon is travelling? And we're going to answer in terms of c. So the first thing we can do is simply use our question 10, self-centered. So question 10, the formula is TV equals gamma T naught. So we know that the dilated time is 6.8 milliseconds. Don't forget, when using this formula, we can use units which are not standard units because as long as they are the same on both sides, they should cancel. And gamma is what we're about to find. And the normal time, the proper time, is 5 milliseconds. Okay? So there's the units on both sides, which are exactly the same. So therefore, they can cancel. This gives us that the gamma is 6.8 on 5. So 6.8 divided by 5 gives us 1.36. Don't forget, gamma must be greater than 1. So if you've got this as a 0 point, you've done the wrong division. Okay, it's upside down. Okay, so now we want to find the velocity that we've got. Now, gamma is equal to 1 over the square root of 1 minus, and normally there's a value here which is squared, okay? And that is, in the formula, is v squared over c squared. But we don't use that. We use a decimal like, 0.93c or something like that. So what I'm going to do is, to make this easier for us, we just simply put in a number, a letter, an algebraic value here. I'm going to use k, and this is going to be the decimal, the decimal of light. So in this case, we're just going to find k. So that's going to be 1.36 is equal to 1 minus k squared there. So the square root of 1 minus k squared would equal 1 over 1.36. That's just the reciprocal of that value there, which in this case is going to be, let's get the, oops, that's equals, I've got to do that again. 1.36 reciprocated. Okay, so that's it. So it's 0. Put it up there. Okay. 0.73529 dot dot dot. So that's 1 minus k squared. We now need to square both sides. So squaring both sides gives us 1 minus k squared equals 0.54065. Keep as many decimals as possible. Don't clear. Just don't round. Round only once at the end. That gives us k squared would be 1 minus 0.54 and so on. So 1 minus this value over here is equal to k squared would equal 0.4593. Finally giving us k as the square root of that number. So the square root of that value is 0.6777. Okay, and that gives us that this is the decimal of light. So we're actually traveling at 67.77% of the speed of light, or 0.6777c. Rounding it to an appropriate level, that should be 0.68c. Okay. This little secret of just using a k value here makes this so much more straightforward than using this fraction over here of v squared on c squared, because k just stands for this coefficient here. Okay. And going up to question 11. Question 11 said a clown is known to be able to clap his hands 4 times per second on Earth. When traveling on a spacecraft, observes him clapping at 2 times per second. Okay. What is the percentage of the speed of light that the spacecraft is traveling? Well, what we've got here is a frequency. So the clown has a frequency of 4 hertz on Earth, which means the period of claps between each claps is, remember, frequency is 1 over the period, is reciprocal of that, or 0.25 seconds, which is a quarter. Okay, so this is how long a clap takes on Earth. When it's on the spacecraft, it's 2 hertz, and so the period would be 1 over 2, which is 0.5 seconds. Okay. So this is the stationary value. This is T0, and this is the TV. So this is the time, the dilated time, the longer time. So putting that into our formula, TV equals gamma T naught. 0.5 equals gamma 0.25. So gamma is equal to 0.5 divided by 0.25, and lo and behold, it equals 2. Okay. Now we've got the gamma factor. We can say that 2 equals 1 over the square root of 1 minus k squared. Remember, we're using this little secret, using k here. Squaring both sides or multiplying it up, we get the square root of 1 minus k squared is equal to a half. Squaring both sides, 1 minus k squared is equal to a quarter, or 0.25. I'll start using decimals. So k squared would equal 0.75. So that goes over there, comes over there. And therefore k equals the square root of 0.75. So 0.75, square root of 0.75 is 0.866. And therefore we're traveling at 86.6% of the speed of light, or 0.87 c, if we want to round, or to simply 87% c, rounding, whatever the answers will say. You just round appropriately. Okay. And moving on to question 12. And finally, I just did notice that there is an answer here. I put, unfortunately, put a decimal in that question there. So it's meant to be 48 seconds, not 40 or 47 seconds. Right, so question 12. A stationary observer measures the time taken for a craft to pass behind Jupiter, traveling at 0.99 c, to be 1.2 seconds. How long would the passenger on the craft measure this time? Okay, so what we've got here is that we observe a longer period of time than the person who would be on the craft. The craft would have a normal, they would be measuring a shorter time, but because we observe a longer time, we observe the dilated time. Okay, so the first thing we're going to do is simply work out the gamma factor for this situation. So for question 12, the gamma is equal to 1 over the square root of 1 minus 0.99 squared. And that is 7.0888. Now, TV equals gamma T naught. Always write down your formulas before use. It does help examiners in the HSC to work out what you're doing, and they can give you marks even if you put the gamma and the T in the wrong place. Okay, so the two values here is I have 1.2 seconds. So my choice is put it here or here. Okay, so hopefully by now you've worked out that the person on the craft will think that a shorter time is going to pass. Okay, so we observe a longer time because the craft is in motion. Okay, so this would be the time at velocity. So it's 1.2 seconds passes equals 0.0888 and T naught. Okay. Therefore, T naught would equal 1.2 divided by the gamma factor, which is 0.169 seconds or 0.17 seconds. Okay, so on the craft, they would see that they've passed behind Jupiter in nearly 0.2 seconds, but we observe they think that they have, I've got the wrong way around. So they would see this time pass on thing, whereas we actually observe the time that they would experience as 1.2 seconds. Well, I hope that didn't confuse you too much, that last loss of concentration there by me. Okay, thank you very much. That ends this worksheet.